¡Viva Bolivia! ¡Viva la Sociedad Boliviana de Matemática!
Hola, hola. Tengan todos ustedes muy buenos días. Mi nombre es Alex Pantoja, soy el secretario general de la Universidad Simón y Patiño. Sean bienvenidas y bienvenidos a la Universidad Simón y Patiño, nuestra querida Casa Superior de Estudios que alberga este Congreso Nacional de Matemáticas, el cual está organizado por la Sociedad Boliviana de Matemáticas, Sobolmat. Me complace brindarle las siguientes palabras. Quiero iniciar indicando lo que ya sabemos todos. La ciencia son un conjunto de conocimientos adquiridos por la humanidad, una necesidad del ser humano para su progreso y desarrollo. Estas son un acto creativo del individuo. La gran mayoría de las ciencias están relacionadas con la ciencia, el lenguaje del universo, la matemática. Esta les ha aportado criticidad, les ha permitido el desarrollo de grandes teorías y aplicaciones. Basta estudiar alguna de ellas, en particular para ver su huella plasmada en el fantástico concierto de sus teorías, que dan muestra del profundo poder de creación que tiene la figura más compleja del universo, el ser humano. Quiero hacer énfasis también en la importancia de la enseñanza de la matemática, en todos los niveles educativos. Especialmente en estos tiempos de COVID, el mundo se ha dado cuenta que cobra más importancia el problema de la enseñanza-aprendizaje de la matemática, pues una buena metodología conllevaría a nuestros estudiantes a ver la matemática como una ciencia esencial, bonita, prioritaria y clave para el desarrollo social, económico y político de Bolivia. Y podría permitir la formación de nuevos cerebros matemáticos. Además, lograríamos que nuestros alumnos no sigan viendo a la matemática aburrida, abstrusa, inútil, inhumana, muy difícil, como un conjunto de temas misteriosos, desconectados de la realidad, que no se entienden y sin ninguna aplicación. Y le quitaríamos definitivamente a la matemática esa reputación de presumida e inalcanzable que se le ha dado por muchos siglos. Como profesionales, y muchos de ustedes futuros profesionales amantes de esta ciencia matemática, tienen la responsabilidad de construir más y mejor conocimiento y a través de estos resultados cambiar a la sociedad. Quiero concluir estas pequeñas palabras con una frase de Einstein que hablaba respecto a esta ciencia. Las matemáticas puras son, en su forma, la poesía de las ideas lógicas. Con esto quiero dar paso a nuestro estimado rector y presidente de la Sociedad Boliviana de Matemáticas para la inauguración de este magno evento. Doctor.
Estimados colegas y estudiantes, a la fecha son 30 años de vida que tiene nuestra Sociedad Boliviana de Matemáticas. Desde su fundación, el objetivo principal de la misma fue fomentar el crecimiento de la disciplina matemática en nuestro país. Y pienso que la Sobolmat ha logrado ese objetivo. Sin embargo, queda todavía mucho por hacer. Debo señalar que un mecanismo fundamental para consolidar Sobolmat es la unidad. Debe ser la unidad. Soy consciente que a lo largo de nuestra existencia han habido ciertas desavenencias entre sus miembros. Pero importantes acercamientos que consolidan a nuestra institución. El rótulo del presente congreso es la matemática en tiempos de COVID. Observamos que existen pocas charlas sobre esta temática. Si bien la misma es una temática muy vigente, puesto que todavía estamos planetariamente afectados por la pandemia del coronavirus, que tanto daño ha hecho a la humanidad en varios aspectos. Sin embargo, la mayor parte de los expositores y del presente Congreso se sumergirán en el mar de la matemática y abordarán numerosos temas del quehacer matemático puro y aplicado. Existen pocas charlas en el presente Congreso que tratan sobre la educación de la matemática. Por lo tanto, anuncio que el próximo año organizaremos un congreso especial sobre esta temática. La Sociedad Boliviana de Matemática agradece su presencia al 23º Congreso de nuestra institución y hace votos para que nos unamos y trabajemos más por el desarrollo de la matemática. Reciban un gran abrazo de mi parte. Muchas gracias.
Okay, so can we go back one slide? Go back one more. So let's start. This is a good point to pick up. Okay, so the first element, as we said, is this notion of the reduction principle, and there are two alternatives. One where greater mixing reduces growth. Okay. And then the other is where you, by the greater mixing, doesn't change things. Okay, so before I go further, let me just say here, so what this is telling you in the first case is that then you would be selecting for slower movement in an evolutionary way. Okay, but there are lots of examples where you would be selecting for positive movement because movement is going to become necessary to survival. So and so the idea here is both of these things should happen. And so the question is going to be, when does the first happen and when does the second happen? And Hastings' work that I'm going to speak to now is predates the work that Altenberg did, which was 2012, even though he worked on it extensively before that. But it is a prime example of what he was getting at in terms of the what's called here the slower disperser is going to prevail. So let's go back here. So this is the paper in theoretical population biology that goes back to 1983. And so that what he's going to show is that if I've got random dispersal and logistic growth dynamics, the slower dispersal can always invade an ecologically identical faster dispersal. So he's looking at a model of the form UT equal alpha Laplace U plus U f of XU in a domain, some spatial domain with Neumann, or in this case, no flux boundary conditions. And is going to assume that the local per capita growth rate F is decreasing in the density. That's the logistic part. And then what is well known is that under appropriate conditions on f of x and 0, for example, that its integral over the domain is greater than or equal to 0, then you will tend to a spatially very positive equilibrium. And so then the idea, and he did this with only a single equation, if we introduce an ecologically identical variant so that you've got the same F, and moving randomly at a rate when U is near the equilibrium for the resident, then the variant will be able to increase its density if and only if it's moving slower. And here then, what this is going to say that this operator of the form A alpha plus B, where A is the Laplacian and B is the local per capita growth rate, our surrogate for reproductive fitness, that this will satisfy the first of the alternatives that Altenberg identified. Then 15 years later, in a paper by Dockery, Hudson, Mashaikal, and Penarowski in the Journal of Mathematical Biology, they formulated it in terms of a competition model between two ecologically identical species, where all that's different in the model from one equation to the other is that the diffusion rate for the on the species with density U is alpha, and that for the species with density V is beta. And these are to be subject to no flux boundary conditions. And then what they show is that if you the U will drive the species with density U will drive the species with density V to extinction if beta is less than alpha, independent of the initial distribution of the species. So here in this problem, the Dockery et al. Do specify f of xu as the local, the density of resources minus u, but the horizontal O's in general. And the key here is having m of x non-constant, okay? And as I said, this is an example in which the first alternative of the reduction principle holds, and diffusion at rate beta can competitively exclude any faster random dispersal strategy. Okay, there's some key observations here. Notice that earlier I had said that when I was talking about when you could possibly have the second alternative, when I would say you had an eigenvector so that A U star is equal to 0, and then f of x U star is equal to 0. Okay, so that the overall equilibrium is an equilibrium by being one for the dispersal part and by being one for the reproductive part simultaneously and independent of each other. And that does not happen in the case with random movement, if so long as the resource function m of x is non-constant, because if you were to have a solution to Laplace U equal to 0, with these boundary conditions necessarily a constant, and so no constant could then be equal to m of x. So that can't happen there. So that this means then that the equilibrium in the corresponding logistic model arises through a balancing of demographics and dispersal, and not in a way that we know that we could conceivably have that and get the second alternative. And moreover, what one can show by a linear perturbation analysis is that a slower rate of random movement produces an equilibrium that's closer to the spatially varying equilibrium of the kinetic problem, where we have space, but we don't have any movement. And what this means is that closer matching to resources is what's leading to the competitive exclusion that one is getting to. So there are numerous situations in which organisms have to move to survive. So it is reasonable to expect instances in which higher rates of dispersal should be advantageous over lower rates. And so the history above suggests that in models in which dispersal and demographic are separate additive terms, such as in the model I've been showing, and dispersal is linear, one should look for dispersal operators where the equilibrium of the kinetic model is also in the null space of the dispersal operator. And as we noted, this cannot happen with purely diffusive dispersal. Okay, since our discussion so far has been focused on reaction diffusion model, let's take this as a starting point. So the upshot of what I just said is that I can't get this kind of advantageous second alternative with purely random motion. So I've got to add some additional component beyond random movement. And so a natural place to think is to add advection of the gradient of the resource. Okay, where it's, and what that means is that you would be moving to areas where, or regions where you would have more abundance in resources or more availability here. And indeed, if the rate of advection of the gradient is low to moderate, it can sometimes permit a faster a species that combines faster diffusion and advection to outcompete and exclude an ecologically identical competitor, so reversing the prediction when it's not there. But what typically can happen here is that as the rate of queuing on the resource gets large, the species will concentrate so heavily, move so in so pronounced a way to the good parts of the habitat that it leaves other resources on the table for the for its competitor to make a living on. And so that then you get in here, then you get a form of spatial segregation whereby the species dispersing randomly can stably coexist with its competitor. And we term this advection-mediated coexistence. So just advecting up the gradient of a resource, that can lead to some advantage at some rates, but it's not going to be something that's going to be independent of rates. And so you can get around this by modulating the speed of the advection by not advecting up its gradient, but rather by advecting up the gradient of its logarithm, assuming that's positive throughout the habitat. And the reason being here, if you look at the equation where now we've got the gradient of log n that we're advecting up, of course, that's the same thing as the gradient of m over m. Okay, and so you're not changing the direction, but you're changing how fast you're doing that. If resources are comparatively better, you're going to move a little more slowly. And subject again to no flux boundary conditions. And so this then gives you a case where I've got, if I take A to B, mu del dot grad u minus u log m, and then f of x u be m of x minus u, then I'm going to get U star equal M will satisfy A U star equal to 0 if we go back. So if you look here closely, you would have grad M over M, so that when I plug in M here, I get grad M, then I've got M, grad M over M, the M's cancel, and I've got grad M minus grad M. And so that then I get this part to be zeroed out by the choice U equal to M, and I get this as well. So I've got something that satisfies the second alternative to the reduction principle. And moreover, we can prove that in this case, the species following this strategy will competitively exclude an ecologically identical competitor using a different dispersal strategy. And notice here, a fascinating part about all of this is that the dominant dispersal strategy is generated on the basis of only local information, but then it has conclusions about what happens on the scale of the larger habitat. Okay, and also this relates to the Weber-Fechner law from psychophysics that's going to tell us that the intensity of our sensation increases as the logarithm of an increase in energy rather than as rapidly as the increase, so that we are actually, and then there are experiments on chimpanzees that back this up, that we process information on that kind of thing. So the question here, so I've now said that if we add in advection of the gradient of the logarithm of the resource density, and we add things together appropriately, we get something that, one, satisfies the second part or the second alternative of the reduction principle, and it's also the case where then a species utilizing that strategy will eliminate any competitor, ecologically identical competitor that uses a different one. Okay, and so the question is then how to explain this, and so there are three concepts behind this. One from game theory, one from math, and one from ecology. The first being the notions of evolutionary stable or steady strategy and a neighborhood invader strategy borrowed from adaptive dynamics. The second is the mathematical notion of a line sum symmetry and its functional analytic generalizations for appropriate composition of dispersal and demographics that vary from different regimes that you're modeling one to the other. But these are the tools that help us to get the signs and the eigenvalues that we need to conclude who can invade and who can't, and then also to help show that you can't have coexistence of the two things at equilibrium. And then, but the third is an ecological construct that I learned about in the process of doing all of this. It's called the ideal free distribution. It goes back to Fretwell and Lucas in a biology journal called Acto Theoretica in 1969. And their work grew out of observations about large birds of prey, such as eagles or ospreys or hawks, such as this. And they have among all species probably among the strongest ability to, one, sense the totality of the landscape that they inhabit, and two, then be able to move freely within the landscape where they want to go. And so the notion of Fretwell and Lucas is that when organisms can assess the environment perfectly, that is the ideal part, and can move freely, that's the free part, they're going to distribute themselves so as to maximize reproductive fitness. Now, this was a purely ecological construct here. And so it was verbal ecological theory. My long-term collaborator of 40 years, Chris Gosner, in conjunction with biologist Mishat Kshatriya, was among the first to formulate this ideal free distribution mathematically in a kind of context. But it's also interesting just to observe that this does not necessarily involve population dynamics, so having to do with reproductive fitness here. It's something that we all actually probably have likely experienced in our own lives. Next picture. So this is a famous picture of stickleback fish in an aquarium tank. And they are on each side, they're being fed water fleas, or what are called daphnia. And what you see here on the left side, there are multiple little black dots representing the daphnia, whereas over on the other side, there's like only one. And so you just start dripping in, and then you put them in there. Then eventually what's going to happen here is that the majority of the fish are going to congregate over underneath where lots of daphnia are being dropped, and whereas a smaller number here, only one, that will congregate over here, so that they are getting equal resources at each time. Another way you can think about it is something like if you are waiting in a line to buy a movie ticket, or to pay for parking at an airport, or any number of things, and you get a choice of lines, and you frequently, or in my case, almost always will be the case that I somehow choose the line where the person in front of me has some extra issue. But this is the idea. You're distributing yourself so that you get equal use of resources, or if you think of it in a population dynamical context, where fitness is being equalized. Next slide, please. But what it does require, and this is the key thing, is the fitness on an individual level is equal throughout all occupied locales. That is, the fish under the one is getting as much as the fish that are under all of the others. Okay. And so the idea here is, if not, some individual is going to move to improve fitness. So that would allow individuals to exchange places, but no net movement. And if you take population dynamics into consideration, the fitness is going to have to be zero, otherwise everybody's going to continue to grow. So it means that in models of this form, the condition A u star equal to 0 and f of x u star equal to 0 does correspond to an ideal free distribution. Next slide, please. And this, and again, reminds you that then you got the that in this reaction diffusion setting where you were adding on advection of the gradient of the logarithm of the resource, that then you got the competitive exclusion of any ecologically identical competitor that using a different dispersal strategy. And there's a robustness going back to the very first slide across model formulations. It's established in reaction diffusion, advection, integral differential and non-local, packed models, metapopulation and natal dispersal, integral difference, matrix models. Some of these I participated in. Okay, so this is bringing us up to closer to the present. So allowing temporal heterogeneity in models. Everything that I've said so far has not had the movement and the fitness aspects are independent of time. And so one wants to allow both temporal and spatial heterogeneity. And so this is work that I did with Custer. And we started out in just in one space dimension looking at this, so that what we want to do here is then allow the quantity that we would be vecting up, this p term, to be depending upon t, and then the growth the resource function to depend upon t. Okay, again, subject to appropriate no flux boundary conditions. And I'm going to require P and M to be smooth and T periodic in time. And again, where I take M to be positive in both space and time. It's well known, going back, a good reference is the book of Peter Hess in 1982, that there is a unique positive T periodic solution to this problem that will be the global attractor of the model for all non-negative, non-trivial initial data. And it's natural then to assert natural extension of what we had before, to assert that the model admits an ideal free strategy whenever M of xt is the periodic orbit in question. So in such a case, then I'm going to have M sub t for mu mx minus m p of xt sub x on the interval plus positive time. And so there's no net movement then when population density perfectly aligns with resource distribution through space and time. The question is whether this is possible and under what conditions. Okay, so can I get such an advection function so that I get the result about M? Well, in one space dimension, P of xt is necessarily a spatial gradient. So we can solve the left side of the boundary conditions to get the P of 0 and t would have to be mu times the derivative of log of m of x, 0 and t. And so then we integrate the equation for M, and then what we have to have is that the resulting function P of x and t has to be t periodic in time and satisfy the second boundary condition. And what one can go through and do is just doing the calculation from the, go back one just for a second, please. So that if we look at equation 11, and we solve that for P, okay. And so then we can write out the candidate. And notice here that if there was no dependence of M on T, this term would go away. And then what I would get P of X would be then M prime over M, again, that being then the log, the derivative of the log of M. Okay. And so, but then, but M is T. So since M is T periodic in time, there, okay. Since M is T periodic in time, so is P. And what we end up here is that P will depend on non-local as well as local information about the resource distribution. And so what we can see here is we try to calculate the second boundary condition. This is going to hold if the integral over M of Y and T over space is constant in time. So in that case, then the P is then going to be an appropriate function. Okay, and so we need to require the total amount of resource to be constant in time. Now, this is a non-trivial constraint, but it is possible under some plausible situations. For example, when a peak moves back and forth across the landscape. So, and we can also show that in this case, an ideal free strategy will competitively exclude an ecologically identical competitor using a non-ideal free strategy. And this can actually be extended to higher space dimensions. So there's nothing special about one space dimension. It was just easy to see that. So this is a reasonable start. That is, that allows you to get a perfect match with in the same way that you would have in the case where you were in a spatially heterogeneous but temporally constant setting. But we need to address issues in trying to interpret the concept of ideal free distribution and understand the evolution of dispersal in environments that vary in both space and time. And so it's not immediately clear how individual fitness or an ideal free distribution should be defined. So using the local per capita growth rate as a proxy for fitness is going to be inadequate in time varying environments where the fitness of an individual depends not only its location, but also how it's moving through space and time. And an IFD and a static environment can be defined in terms of the habitat selection that optimizes fitness, but in a temporally varying environment, the timing of life history events is also. So this is going to be good to the setting where we want to meet the problem, where we now will write the instead of having the m of x minus u, I'm going to write this where I write out the local growth rate and the carrying capacity as separate quantities. That is the r of x and t and the k of x and t. And so those are going to be, we'll think of those as the environmental functions, local intrinsic growth rate, and carrying capacity. And then the choice mu of x and t and p of x and t to constitute the dispersal strategy, that is the diffusion rate and the vector field describing directed movement respectively. These coefficients are t periodic in time and smooth, where r, k, and mu will be required to be positive over space and a full cycle of time, 0 to t, near t periodic. So if I'm going to compare fitness of individuals with different strategies, I've got to have a notion here of fitness. And so, and this work now that we're talking about was done with my long-term collaborator, Chris Costner, and also a more recent collaborator, Ian Lamb. at the at Ohio State University. And this is part of what got me through the early parts of the pandemic. So I enjoyed doing this. Working with them was enormous pleasure. So let's start first at a model where there's a spatial location, but you got no room. And here, f of x tu is commonly regarded as a proxy for fitness. And now, if f doesn't depend on t, and either u is fixed, say at equilibrium, or f does not depend on u, then we can interpret f of x u star or f of x as average fitness at the location and use that to model fitness. But we're going to need to take into account what happens through a full period of time as well. So we can still define fitness at a location with a period map describing u of x and t in terms of u of x and 0 from this equation here. And so then if we then look and calculate out what this would lead us to take if we did not have time dependence, then it leads us to conclude that then we could set reasonably the average of f of x and t over the interval 0 to t as the proxy for fitness. And moreover, we've got t fixed, and we're going to be interested in comparing fitness between individuals. So we can drop the scale factor and then just use the interval of f of x t over 0 t as our proxy for fitness. Okay, now, so suppose now that the local per capita growth rate is still given by f of x to t, and it's still still t periodic, but now individuals are not going to remain at fixed locations in our habitat. Instead, an individual is going to follow a path gamma of t for between 0 and t. And here I'm not necessarily assuming anything that the endpoints are fixed. It's just allowed to move any way that it wants. Okay. And then we can take the integral of f of gamma t over 0 t is what we are going to call the pathwise fitness, f's path of gamma. And now we go and specialize to the context. We go back one more to this reaction diffusion equation here. Okay, thank you. And so when the environment is temporally constant, so when R and K do not depend on T, then the stable population will be at equilibrium so that the per capita growth rate depends on X only, and then an ideal free distribution is realized when fitness is equilibrated, and it then will correspond to perfect alignment with carrying capacity. And again, when the environment is T periodic, we expect the population density to stabilize at a time periodic solution so that the per capita growth rate varies in space and time. So that by the equation 16, f of xt, r of xt, 1 minus v star of xt divided by k of xt. Okay, when r of xt equals k of xt, we reduce back to the case in preceding case where k of xt would be m of xt. So we can recover the case with the total carrying capacity of the environment is independent of time. And perfect alignment is not possible without this assumption. And so we can now get the pathwise fitness for gamma in this equation. So now, okay, so suppose that the population achieves an ideal redistribution. So then our expectation is that no individual can gain a proliferative advantage by dispersing itself differently within the time period. So the pathwise fitness should be equilibrated among all possible paths. And so the distribution can be an ideal free distribution if and only if the corresponding pathwise fitness is independent of paths. And so what this does is motivates the following definition of ideal free distribution. Suppose the population stabilizes in a positive periodic solution, V star of X and T, then we're going to say that V star of X and T will be an ideal free distribution if 16 is independent of X. Can we go back? So that when I look at this expression, R of X and T times 1 minus V star of X and T divided by K of X and T, okay, that when that is then independent of X over the domain. And then one can get necessary and sufficient conditions in terms of R and K, whereby an ideal free distribution exists and is both an evolutionary stable strategy and a neighborhood invader strategy. So this then allows us to treat more general forms of logistic growth where the total amount of resource availability in the environment varies periodically in time. So the restriction on the total amount of resources not changing over time can be relaxed, and this puts us into that point. This is most of the next part of what I wanted to say, and thank you for your attention. But if I can indulge you for just a minute more, I have something more that I'd like to share. So I'm very delighted to tell you that we will be hosting the next Mathematical Congress of the Americas in Miami in July of 2025. There will be lots more information forthcoming in the very near future. We are in the process of getting some of our infrastructure finalized at this point. I already sent out an announcement to the institutional members of the Math Council of the Americas, which includes Professor Solagura, and that was how I came to be invited to be here in the first place. So spreading the word also has its advantages. And with that, I offer you my thanks for your kind attendance.
Thank you very much, Cantrell.